Hi, welcome back to our discussion of atmospheric dynamics. And we're going to be talking about the thermal wind in this video. And this is the third video on the thermal wind. So far, we've discussed the concept of thermal wind. We looked at calculations, and now we're going to see what the thermal wind does to our atmosphere. So we already said, this is a quick review, we said that the thermal wind is parallel to the average horizontal temperature gradient in the layer. In other words, it runs parallel with the isotherms, with cold air to the left. And the thermal wind, we saw from our calculation, produces a stronger wind aloft. If you have a weak temperature gradient in a layer, the integrated effect of the sloping pressure surfaces results in a stronger wind aloft, which we call the jet stream. And specifically because this results from a temperature gradient, we're going to call this one the polar jet stream. So the polar jet stream is a channel of fast-moving winds, approximately about 300 millibars, which is 30,000 feet. The polar jet stream typically is found anywhere from about 30 degrees north latitude to about 60 degrees. You also find it in the southern hemisphere. It goes all the way around the poles and it circumnavigates the Earth, both in the northern hemisphere and also in the southern hemisphere. You can see where the polar jet stream dips down, that's where you have a trough, and also that's cold air. Where it dips up, that's where you have a ridge, and that's relatively warmer air in that layer. So the horizontal temperature gradient from the equator to the North Pole results in sloping pressure surfaces. We talked about this already. This is from your hypsometric equation. Where the air is warmer, the pressure surfaces are farther apart. Where the air is colder, pressure surfaces are closer together. So at the North Pole, you have lower heights, and at the equator, you have higher heights for any given pressure surface. That means the pressure surface is sloping, which means that there's a height gradient. And we saw that height gradients result in winds. That's part of the geostrophic wind equation. Your height gradient over some given distance produces a wind. So you can think of the jet stream, the polar jet stream, as separating the cold air at the North Pole from warmer tropical air down south. And then super embedded within the jet stream, you'll find these fast-moving regions of wind. We call these jet streaks, and they're embedded within the polar jet stream. And they're a little bit faster, a little bit stronger than the surrounding wind speeds. Here's a map showing on a particular day, way back in 2000, a couple of jet streaks across the United States. One stretching from the Gulf of Alaska all the way to Utah, another one stretching from Louisiana all the way up to Quebec almost. So we'll find these strong jet streaks wherever you have a very strong temperature gradient, because that's what the thermal wind says. Where you have a strong temperature gradient, you have a strong wind aloft. And so the strongest location, the location of the strongest temperature gradient in our atmosphere is in regions called fronts. Fronts, you have a temperature gradient, temperature change across the front is significant. So as a result, that produces a height gradient aloft, which produces stronger winds. So that gives you a little bit of insight as far as why we study the thermal wind and the applications to it. And we have one more video where we're going to look at the thermal wind.